Let's look at that problem that you voted off the island. That problem is obviously an old exam problem. It has 15,000 parts. Okay. You compress a spring by an amount 1/2 meter, and then you release the spring by letting go of the block that's up against the spring, and you find that as the spring releases, it sends this block along the frictionless part of the track, and it's going 6 meters per second after it leaves the spring. We want to find in part A here the spring constant for the spring. Now, if you look at those equations on the right for momentum and impulse, do you think we're going to find a value of K there? Yeah, that's just not the way to go. This is an energy problem, and that means we start with energy initial. I'm going to need some room over there, so I'm going to put it over here. Energy initial plus Vec external is equal to energy final. Now I'm going to call this my initial state. I'm going to call this my final state. Since there's no friction on this part of the track, there would be no Vec done between the initial and final. At the initial event, I asked the same 3 questions I always ask. Is anything with mass moving? No. Anything up off the floor? No. Any spring stretched or compressed? Yes. And then I go to the final event. I ask the same questions. Anything with mass moving? Yes. Anything up off the floor? No. Any spring stretched or compressed? No. That's my equation. I got 1/2 K times 1/2 meter squared is equal to 1/2 times 2 kilograms times 6 meters per second. Remember to square that. The person to your right is not going to do that on the exam. They're going to forget. Okay? That's how prevalent that is. Half of you forget. Okay? Now, that gives me a value of K of 288 newtons for each meter. Now, in part B of this problem, we have a collision. The small block comes in and collides with the large block, sending it off at 4 meters per second. And it travels after the collision along a rough section of track which has a mu sub K of 0.25. Now the first part of the question is just what kind of final velocity after the collision do I have for this little block? Is it to the right or is it to the left? Now, that's a collision, so I use momentum. And it's a vector, so I need a coordinate system. So before the collision, I had 2 kilograms moving 6 meters per second to the right. I had 4 kilograms. I wasted ink. Afterwards, I've got the 2 kilograms. I don't know whether it's moving left or right or how fast, so I make that a positive variable. And I've got the 4 kilograms moving at 4 meters per second, and it's to the right. So that's 12 franci plus 0 is equal to 2 kilogram V final plus 16 franci. I solve for V final by subtracting 16 franci, and I get minus 4 franci is equal to 2 kilogram V final, or V final is equal to minus 2 meters per second, or 2 meters per second left. Now, the next part of this problem is asking what type of collision is this? Elastic, inelastic, or maximally inelastic? Well, we know, not that collision, that's maximally inelastic. We know that this collision can't be maximally inelastic because the big block is going 4 meters per second that way, and the little block is going 2 meters per second to the left. They're not traveling together. But how do we know if it's elastic or inelastic? Well, some people just like to look at it and say, you know, that looks inelastic. Or, you know, the little block's not moving as fast as it was before. That's probably inelastic. Here's the thing. There's nothing you can look at and tell. You can't sniff the air and know whether that's elastic or inelastic. You have to do a calculation. You have to find the initial kinetic energy before the collision. That's going to be 1/2 times the 2 kilograms that was moving at 6 meters per second squared, plus 1/2 times the 4 kilograms that wasn't moving. Remember to square it. Okay, that's going to be 36 joules plus 0. Afterwards, I have 1/2 times 2 kilograms. It's going negative 2 meters per second. The minus sign doesn't matter because I'm squaring it. Plus 1/2 times 4 kilograms times 4 meters per second squared. This is going to be 4 joules plus 32 joules is equal to 36 joules. This is a once in a blue moon experience. The kinetic energy is conserved. You didn't know that when you started the problem, so you best have used momentum. Okay? It's just a happy day that it happened to conserve energy as well. Now the last part of this problem says, for how many seconds does this big block scrape across the rough section of track? Well, since we're asked for how many seconds, it's momentum. And since it's no longer a collision, the collision's already happened. And now we've just got that block scraping across the table, or the floor. In that case, I have to use the general equation here, and that's going to be P initial plus my force delta T is equal to P final. I need a coordinate system. My initial momentum before it starts scraping is going to be 4 kilograms times 4 meters per second, and it's to the right, so it's positive. The force that is going to change that momentum down to 0 is the friction force, kinetic friction by the floor on the block, times the time. Now, if I knew what that friction force was, I'd be done with this problem. Well, I've known how to find forces. You draw a free body diagram. You have a weight force on that block, which is 40 newtons. You have a normal force on that block, which is 40 newtons. There's no acceleration up or down. You have a kinetic friction, and that kinetic friction is going to be mu sub k times the normal force. That's going to be 0.25 times 40. And that's 10. So if I come in here and I say I've got plus 16 Franci minus 10 newtons, delta T is equal to 0. Delta T is equal to 1.6 seconds. See if your neighbor got that right when they did their homework. If not, you know what to do.